In Lesson 2, we're going to solve systems algebraically. Systems that have the same solutions are known as equivalent systems. In real-life applications, you can have a system of equations, and they'll oftentimes have solutions that are not exact integers. Let's consider the rental car industry, which is the better value when you're renting a vehicle. So if you rent a hunk of junk, they charge $29.95 a day and 43 cents a mile. But Tom's Total Rex charges $45 per day and 32 cents per mile. If you knew when the costs were the same, you could easily determine the better value for your individual needs. So we'll revisit some practical applications later in the lesson. First, we want to look at solving by the substitution method. And without reading the steps, I'm just going to jump into the first example and use those steps to solve using substitution. So I like to number my equations, equation 1 and equation 2. And then we would want to pick one of the equations to isolate for a variable. So let's say, for example, that we're going to take equation number 1 and we're going to get x all by itself. So equation number 1 would have x equals 5 minus 3y. And by doing that, I can take equation 1 and substitute that expression into equation 2. So in equation 2, we have negative 2 times x minus 4y equals negative 5. So what we want to do is we want to take this name for x, which is 5 minus 3y, and substitute that name for x into the place for x in equation 2. Now we can solve for y. So we have negative 10 plus 6y minus 4y equals negative 5. So 2y is 5 and y is 2.5, or 5 halves. So y is 2.5. And if we know y is 2.5, we can substitute again that value for y back into equation 1 and solve for x. So x is 5 minus 3y when y is 2.5. So 5 minus 7.5 tells me that x is negative 2.5. So we've used the 3-step process to solve for our point of intersection. X is negative 2.5 and y is positive 2.5, and we have that unique solution there. In example 2, an online music company offers 15 downloads for $19.75, and then 40 downloads cost $43.50. Each price includes the same one-time registration fee. So if we relate that, we have 15 downloads and some kind of a fee. So 15 downloads plus a fee, and that's going to cost $19.75. Or we could have 40 downloads and the same fee that's being charged for $43.50. So if we define that and let D stand for downloads and F stand for fee, we have 15D plus the fee, F, is $19.75. That's equation number 1. And then equation number 2 is going to be 40D for downloads plus F for the fee, and that would cost $43.50. So another approach is we can solve by subtraction, because you notice that you have plus F and plus F. So if we subtracted the two equations from each other, we would have 40D plus F is $43.50. And I could subtract 15D and subtract F and subtract $19.75, and that would leave us 25D is 23.75, and dividing by 25, a download would cost 95 cents. Then substituting the download back into, let's say, equation 1, since it's the smaller equation, 15 times 95 cents plus the fee is 19.75. So we have 14.25 plus that fee is 19.75, and subtracting 14.25, the fee is $5.50. So your download would cost 95 cents, and the one-time fee is $5.50. And in this case, we just use the idea that the two fees, those could be additive inverses if we subtracted one equation from the other. Now that idea leads me to the elimination method, since it's similar to what we're going to do. The elimination method, again, I'm going to skip over the steps and just use the steps to show you how the approach works. So I have one equation here and the second equation here, and I'm noticing that the y variables are opposites of each other. They're already set up to be inverses of each other. The terms are opposites or additive inverses. So once we know that, we can set the equations up like in a column. So if we do 5x minus 8y equals 20 and negative 2x plus 8y equals negative 8, then we can add those columns together. So adding 5 and negative 2x, and then negative 8 and positive 8, and 20 and negative 8. That's going to give us 3x. This will eliminate. That's where the elimination method comes from. And 20 minus 8 is 12, so x is 4. Okay? So we took equation 2 and added equation 1 to it and found out x is 4. So that's a third equation. Now take the other equation. Let's take equation 2. And we're going to put 5 times x minus 8 times y, and that's going to tell us it's 20. Well, x is 4, so 5 times 4 is 20, minus 8y is 20. And subtracting 20 on both sides, we have negative 8y is 0, so y is 0. That gives us a fourth equation, and the last two equations, 3 and 4, put together as an ordered pair. This is my solution. So our two lines will intersect at the ordered pair 4, 0. This next approach, solving an equivalent system, I like to call that linear combinations. And what we're going to do is we're going to use multiplication to create an additive inverse for one of the variables. And then we'll rewrite the system to show that at least one of the variables have additive inverses and add the system together just like we did in example 3. So let's get started with example 4 here. I see that I have a plus and a minus on the y variable. So we could choose, let's again label our equations. This is equation 1 and this is equation 2. So let's take the idea that if I multiply equation 1 times 2, we could make additive inverses on the y variables. So let's give that a try. So multiplying equation 1 by 2, we're going to multiply every term by 2. So 3 times 2 is 6, and negative 1 times 2 is negative 2y, and 8 times 2 is 16. Now, I will caution you, be careful, because a lot of times you'll forget to multiply the constant on the right side, but you've got to multiply all three terms, the 3, the negative 1, and the 8. And then lining up equation 2 underneath, we have x plus 2y equals 5. So you notice we have the additive inverses right here in the y column. So adding the columns, 6 plus 1 and 2 minus 2 eliminates, and 16 plus 5, that's 21. So we know our ordered pair, the x value is 3. Then you can go back to the original equations, and I'm going to choose equation 2 this time. X plus 2y equals 5, but we know x is 3. So substituting 3 for our x, 3 plus 2y is 5. Subtracting 3 from both sides, we found out y is 1. So you want to check your solution to make sure that your ordered pairs actually are true for both instances before you say this is my answer. So I know 3 times 3 is 9, minus 1 is 8, that's true. And 3 for x plus 2 times 1 is 2, and 3 plus 2 is 5, and that's true. So then you know you've done your work correctly before you move on. Let's try one more together before you go on your own. So in this case, we don't have anything that has additive inverses for the opposite signs. These are both positive. These are both positive, and we need to eliminate either the x or the y. So my choice is, again, I'm going to eliminate the y. And to eliminate the y, the first thing I want to do is I want to take equation 1 and multiply it by 2, and then I want to take equation 2 and multiply that by negative 7. Now, do you understand why I want to do that? Because we're going to make inverses, and 7 times 2 is 14. So multiplying the equation 1 by 2, 3 times 2, 7 times 2, and 15 times 2, and then multiplying equation 2 by negative 7, 5 times negative 7 is negative 35. 2 times negative 7 is negative 14, and there you can see our inverses. And negative 4 times negative 7 is positive 28. So we want to eliminate the y's, and we've done that with negative 29x equals 58. So x is negative 2. And then go back to your original system. It doesn't matter which one you pick. I'm choosing equation 2. The numbers are smaller, and I want to put negative 2 in place of the x. So let's figure that out. 5 times negative 2 plus 2y equals negative 4. So if negative 10 plus 2y is negative 4, then 2y is 6 and y is 3. So again, I have my solution, x, y, but we want to check that solution to make sure that we haven't made any mistakes. Is 3 times negative 2, that's negative 6, plus 7 times 3, that's, 21. That does check out to be 15, so we know equation 1 is true. And then 5 times negative 2 is negative 10, plus 2 times 3, that's 6. And yes, that one is true as well. So we know that we have found the right solution. Moving on to part B, I would recommend you turn off the video and try part B on your own. Then come back to check your work with my work. Now in part B, my idea is again to eliminate y. It won't always be that way, but I see opposites on the sign. So if we multiply the top by positive 9 and the bottom by positive 5. That would give us 45 and negative 45. So 9 times 7 is 63. 9 times 5 is 45. 9 times 2 is 18. 8 times 5 is 40 on the x. Negative 9 times positive 5 is negative 45. And 17 times 5 is 85. So we still have equivalent systems with equation 1 and equation 2. But adding that system eliminates y, and 63 plus 40 is 103. And 85 and 18 is 103. So x is equal to 1. Going back to the original system, I'm choosing equation 1. 7 times x plus 5 times y is 2. So 5y is 2 minus 7. 2 minus 7 is negative 5. So y is negative 1. And I'll leave the checking to you. I believe the solution is positive 1, negative 1 for my x and y point of intersection for this system of equations. In our last two examples, these can be a little tricky. We want to find the solutions and give an explanation for why we have these unique solutions. So equation 1 and equation 2. Let's see. We don't quite have opposites, but if I take equation 2 and either divide by 2 or multiply by a half, we would get negative x plus y is negative 2 for our equation 1. And then 2 times a half is 1. And negative 2 times a half is negative 1, and 0 times a half is 0. So we have equivalent systems. We're going to add them up, and we eliminate x, and we eliminate y, and negative 2 plus 0 is negative 2. So we have a false statement here. You notice all the variables were eliminated. So the variables are gone. I'm going to just write that down to give an explanation. We eliminated the variables and we have a false statement. So these are parallel lines. This is going to turn out to be parallel lines. So the lines are parallel. There's no solution. Anytime all of the variables disappear and your statement is false, you have parallel lines, no solution. Then part B, can you see that one equation is just a multiple of the other equation? If you thought about this, 4 times 3, 1 times 3, and 6 times 3. If you see that, you can know that you have coinciding lines since they're the same. But if I choose to say 4x plus y equals 6, and then I choose to divide or multiply, whichever way you want to think about it, by negative 1/3, or divide by negative 3, multiply by negative 1/3, we're going to end up with negative 4x and minus y, and that's equal to negative 6. So when everything eliminates again and we get, oh, even the constants are eliminated, this statement is true, where this statement was false. So this time the variables eliminated, and we had a true statement. 0 equals 0. That tells us we have coinciding lines without graphing. And that means our system has infinite solutions. Okay? This is the end of lesson 2. And good luck with your practice.